Okay, this is chapter 8.4, finding sums of infinite geometric series. The essential question here is, how can you find the sum of an infinite geometric series? What you will learn in this chapter or video is finding partial sums of infinite geometric series and finding sums of infinite geometric series. So you're going to find the sum of the series and partial sums. So let's take a look. Okay, before we start, what is a partial sum? So it says here partial sums of infinite geometric series. The sum S sub n of the first n terms of an infinite series is called a partial sum. The partial sum of an infinite geometric series may approach a limiting value. Okay, so that's what we're going to take a look at. So let's get rid of this. And here's example one. So it says, consider the infinite geometric series 1/2, 1/4, 1/8, 1/16 plus 1/32 plus ... It goes on forever and ever and ever. It says find and graph the partial sum S sub n for n equals 1, 2, 3, 4, and 5. Then describe what happens to S sub n as n increases. So how we're going to do this is we're going to take S sub 1, and S sub 1 is our first term. That is 1/2. So if you're adding nothing to the first term, the sum of the first term is simply just the first term, then you just get 1/2. So S sub 2, that means the sum of the first two terms. Well, that's going to equal 1/2 plus 1/4, which equals 3/4, right? 1/2 is 2/4 plus 1/4 is 3/4. So S sub 2 is 3/4. Okay. And since this is in decimals, that's also going to be 0.75 if you convert that to a decimals, because we're going to graph on a decimal grid. Okay, so then we're going to go, the sum of the first three terms would be 1/2 plus 1/4 plus, and the third term is 1/8. So this would be 4/8. I'll erase this after, but if we make these all eights so we can add them, 1/2 is 4/8. 1/4 is 2/8, and 1/8 is still just 1/8. And when you add those up, 4 plus 2 is 6 plus 1 is 7. Well, that is 7/8. So let me now just get rid of this. So this adds up to 7/8. And if I put that in my calculator, 7 divided by 8, which is 7/8, it is a 0.875. So this is equal to 0.875. Then we'll do S sub 4. Well, what is S sub 4? Well, it's the first term plus the second term plus the third term plus the fourth term. So really all you have to do is take the sum of the first three and add one more. So let's do that. That makes it easier. I'm just showing you, see these three terms here. So 1/2 plus 1/4 plus 1/8 plus, and then the last term is 1/16 in this case. What we're really doing is just adding 7/8, because that's what these three are 7/8. So these three are 7/8. So really this is the same as saying 7/8 plus 1/16, which was 14/16 plus 1/16. So that's going to equal 15/16. And if I get my calculator out and take 15 and divide it by 16, and I get the decimal 0.9375. Okay, and let me just erase this sketch work, my scratch work. And then S sub 5 is the sum of the first five terms, which is 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1/32, which is the fifth term right here. So as I said before, you take the first four terms, sum, and just add the last one to it. So that's the same as 15/16 plus 1/32, which is 30/32 plus 1/32. So this is going to equal 31/32. So look what's happening. 3/4, 7/8, 15/16. The denominator's doubling and the numerator's getting greater by, or following it, but it's staying one less. So double 4 and you get 8, and the numerator is one less. Double 16, or double 8 and get 16, and 15 is one less. Double 16 and get 32, and 31 is one less. So the next one would be 63 64ths. The next one would be 127 over 128, and so on and so on and so on. So once you see patterns in these, you can continue them. So what is 31 32nds as a decimal? 31 divided by 32 is 0.96875. 0.96875. So now let's graph these. So when I plot 1 as my subscript here, the number of terms is my x. So when s sub 1, when this is 1, I had a half. So you go over 1 and you go up to a half, which is right here. Okay. 2.75. So 2.6.7.75 is right here. 3, go over to 3 and up to 0.85. This is 0.875 right here. 4 is 0.9375. 4 is 0.9. Oh, this isn't right. 0.8 is here. 0.9 is here. 0.85 is here. 0.875 would be right there. Okay. Got that fixed now. And then 4.9 is right here. 0.95 is here. So 0.9375 is about here. And then finally 5 is 0.9. 0.95 is here. 0.96 is about there. So as you can see, this is coming up and it's starting to flatten out. So once we get these plotted from the graph of S sub n, it appears to approach 1. We're getting closer and closer to a horizontal asymptote. So let me show that with this. And so let me draw it as a dashed line and at 1. So here is 1. So this function is coming up and it's getting closer and closer and closer to 1, but it's never going to get there. 1 million over 1 million and 1 is still less than 1. You're never going to get to 1. So this partial sum was 0.96875. And what it's doing is it's approaching a infinite sum. Okay, so now that we've done this, you should be able to do problem numbers 3 and 6 on your exercises. Okay, so here's our first core concept, and we're going to start talking about the sum of an infinite geometric series in this section. So it says the sum of an infinite geometric series with a first term of a sub 1 and a common ratio r is given by s equals, the sum equals the first term divided by 1 minus the common ratio. Provided the absolute value of the common ratio is less than 1. If the absolute value of the common ratio is greater than or equal to 1, then the series has no sum. So we need a fraction between 0 and 1, positive or negative, because you take the absolute value. Okay, so let's put this into practice and see if it's more clear. Okay, so here is example 2, and we're going to find the sum of infinite geometric series. And so here is A. So what do we need? Well, if I go back to here, we need the first term and we need to know the common ratio. So what is A sub 1 and what is R? That is the question. Okay, well, the common ratio in a geometric series, well, in this case, the way it's set up, it's what's in parentheses here. It's what is taken to the power of. So our function, our common ratio is 0.7. So that there is 0.7. The leading coefficient here, 3. If A was 1 or I was 1, 1 minus 1 is 0. 0.7 to the 0 is 1. 0 times 3 is 1. So when I is 1, then we get 3. Okay, so that's the first thing we need to do. We want to find what A sub 1 is. And all we have to do is plug in 1. So you would say A sub 1 equals 3 times 0.7 to the, and then I is 1 for the first term, and then subtract 1. Well, that's going to equal 3 times 0.7 to the 0. Well, 0.7 to the 0 is 1. 3 times 1 is 3. Okay, so now let me just erase this and move this over. So a sub 1 is 3. And r is 0.7. So now we take our formula, and I'm going to go back and look at it. And so it's s equals the first term divided by 1 minus the ratio. So s equals the first term, and let's write that so we remember it, over 1 minus r. So therefore s equals, so you write your formula, substitute your givens, simplify, and solve. So the sum of this ratio, or the sum of this infinite geometric series, is going to be 10. So if I were to graph that, it would just keep increasing and flatten out like we had on the last example, and it would get closer and closer and closer to a certain value that would always end up totaling 10. So there is how you do the infinite series sum. So let's try it again. So our first term is 1. So this time we know what a sub 1 is. Our common ratio is any term divided by the term preceding it. So 3 divided by 1, or 9 divided by 3, or 27 divided by 9. And those all equal 3. So a sub 1 is 1, and r equals 3. So s equals our first term divided by 1 minus our r. So s is going to equal 1 over 1 minus 3 is negative 2. So the sum equals negative 1/2. Okay, and so there you have it. And it's not right. Why is that wrong? What did I do wrong? A sub 1, 1 minus r. R is 3. Oh, here I'm sitting here thinking out loud. I'm not going to stop this video and start over. Okay, so what happened here? I wasn't thinking. Our R absolute value is greater than or equal to 1, so the series has no sum. So it is not 1/2. So I'm going to now erase this. We have to keep in mind, we don't even have to do this now. Right here, you stop and you say the absolute value of r is greater than or equal to 1. Therefore, no sum. Okay, all right, got it. Wasn't thinking. All right, so anyway, here's the next one. First term, 1. R is the second term, negative 3 over 4, divided by first term, 1. Negative 3/4 divided by 1 is simply negative 3/4. Okay, now I've got to think about that. What is the absolute value of r? Well, the absolute value of negative 3/4 is 3/4. And it is less than 1. What did I just hit? Control Z. It is less than 1. So there will be a sum on this one. We didn't get this greater than or equal to 1. So 3/4 is less than 1. So we can continue now and say S equals a sub 1 divided by 1 minus that R. Substitute in our givens. A sub 1 is 1. 1 minus R is 1 minus a negative 3/4, which is positive 3/4. So S equals 1 over, well, 3/4 is 4. 1 is 4/4. 4/4 plus 3/4 is 7/4. 1 divided by 7/4 is just the reciprocal 4 over 7. So the sum of this series is 4/7. Okay, so now you should be able to do problem number 7, 8, and 12 in your exercises. Just keep in mind, if r is greater than 1, you don't have a sum. Okay, example 3, solving a real life problem with the series, sums of series. A pendulum that is released to swing freely travels 18 inches on the first swing. On each successive swing, the pendulum travels 80% the distance of the previous swing. So what is the total distance the pendulum swings? So this is a sub 1. This is a sub 2. This is a sub 3. And this is a sub 4. So we know what a sub 1 is. It's 18. And r, our common ratio, is any term divided by the term before it. So if I take 18 times 0.8 and divide it by, because this is my second term, divided by the first term, the 18s cancel, and our common ratio is 0.8. 0.8 is less than 1, so we will get a sum. So I write S equals a sub 1 divided by 1 minus r. S equals the first term divided by 1 minus r. S equals 18 divided by 1 minus 0.8 is 0.2, and 0.2 goes into 18 90 times. So this thing is going to swing until it comes to a stop. And the distance it travels will be 18 inches, and then 80% of 18, which is 64, 6, 8, and 6, 140, 14.4 inches. So 18 plus 14.4 plus a little bit less, plus a little bit less until it slows to a stop. The sum would be it traveled a total of 90 inches. That's really kind of cool if you think about it. So if you've ever seen a Newton's cradle, it doesn't go forever and ever and ever. It slows down. And if you could determine what this value is right here, the percent decrease in distance every time Newton's cradle bounces, then you could find the sum of the distance the balls travel on a Newton's cradle by using this process. Okay, so now you should be able to do problem number 17 in your exercises. Okay, so writing a repeating decimal as a fraction. This is actually really interesting, and it's kind of mind-boggling that you can actually do this. So it says write the repeating decimal as an infinite geometric series. So what does 0.2424 0.242424 and going on and on and on and on equal? Well, if I take the first decimal places 0.24, then I can add 0.0024 to it. Okay, so let me show you what this is doing if we line it up. If I take the first term here, 0.24, and add 0.0024, which is the second term here, I will get 0.2424. And if I add 0.0000, these 4 zeros, and then a 24, which would be 0.000024 here, then I'll get 0.242424. So really all we are doing is putting 2 zeros in place of the term that was before it. So this keeps going and going and going, plus dot, 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 dot. Okay, well, this is a geometric sum of a series. So we're going to take the sum of a series and it equals this repeating decimal. Well, what is that as a fraction? Well, what's the first term? A sub 1 is 0.24. And r is the second term, 0.0024, divided by the first term, which is 0.24. Okay, so let me just get the calculator out and show you what's going to happen here. What are we taking? 0.0024. So turn my calculator on, clear it. 0.0024 divided by 0.24. and that's going to give me 1/100th. Okay, so that's going to equal 0.01. Okay, so now I take my sum of my series, which is S equals our first term divided by 1 minus our common ratio. So you write a formula. A sub 1, my fault. Okay, substitute our givens. A sub 1 is 0.24, and we're going to divide that by 0.01. Okay, or it's 1 minus 0.01, my fault. And then S equals 0.24 divided by, well, 1 minus 0.01 is 0.99. Okay, well, this can be simplified. 3 will go into both. So how many times does 3 go into 24? 3 will go into 0.24, 0.08 times. And 3 will go into 99. Actually, let's do it easier. Then we'll get rid of the decimal. If I multiply this by 100, that is going to be 24 over 99. What am I doing here? I'm multiplying by 100 over 100 to move the decimal place on to 2 places on each numerator and denominator. Now 24 divided by 99 reduces, and 8 will go into 24 3 times, or 3 will go into 24 8 times, and 3 will go into 99 33 times. So the repeating decimal that will give us 0.24 is 8 divided by 33. And that is actually really cool. So if I hit clear here and check it, 8 divide 33, enter, my mind equals blown. All right, so that's really cool, repeating decimals. So after doing this, you should be able to do problem numbers 20 and 24 in your exercises. Okay, so that brings us to the end of a really short chapter section, 8.4. And here are the exercise problems I assigned, and I threw in number 32 and 33 as some review. So thanks for watching. Have a great day.